Hello everyone. Today I'm going to present findings of our research entitled Assessing Effective Pass-Through Depth for Irrigation Scheduling by Water Balance Modeling. Here I have listed name of our research team. I would like to acknowledge and thanks to all of them for their valuable contribution. My presentation will begin with research objectives, followed by study area. Then I will move on to methodology, where I will describe about equipment setup, how water balance study was conducted on lysometer data to estimate actual evapotranspiration, how reference evapotranspiration and crop coefficient of pasture was estimated. Then I will present some findings of the research. As we know, the root depth of pasture that is used for irrigation scheduling has substantial implication in estimating irrigation requirement. Therefore, this research intended to estimate effective root depth of ryegrass pasture to be used to estimate irrigation water depth based on water budget study in non-weighing percolation lysimeters. This study was conducted on Lincoln University Dairy Farm. Lincoln University Dairy Farm is a 160-hectare pastoral farm with two blocks, North Blocks and South Block. As this picture represents Lincoln University Dairy Farm. And our field experiments were conducted on North Block Paddock 7. Here I have listed some of the reasons of why we choose Lincoln University Dairy Farm for the study. It's because this is pasture-based dairy farm, and to conduct water budget study, there are lysometer facilities. It contains soil moisture monitoring systems, and the farm is very near from the climate station. Now let me move on to methodology. Let us look more closely about equipment setup. This research was based on 20 lysimeters data. And those 20 lysimeters were installed in two locations, with 10 lysimeters in one location and 10 lysimeters in another location. The distance between these two groups of lysimeters was 50 meters. And in each group of lysimeters, two lysimeters was about 1 meter in spacing. And these lysimeters were circular in shape with 500 millimeter diameter and 900 millimeter depth. At the bottom of each lysimeter, there was 200 millimeter filter layer. Each lysimeter was connected with a container from its bottom through a pipe to collect drainage. Here we can see container. They are linked to different lysimeters. In the ground, to locate lysimeter, I had used standards that help me to measure grass height on each lysimeter. Ecoflux used for the study was about 100 meters away from first lysimeters in second group, as we can see here. And this ecoflux consisted of two sensors. The bottom sensor was installed horizontally at 500 millimeter from soil surface, and top sensor was installed in inclination. A standard mass balance equation was applied to the lysimeter data to estimate actual evapotranspiration. In this equation, ETA represents actual evapotranspiration. P is precipitation, I is irrigation supply, DP is deep percolation, and SM is soil moisture. A rain gauge was installed near the lysimeters to measure precipitation and irrigation. Deep percolation was measured from the container on daily basis. Soil moisture was estimated based on ecoflux top and bottom sensor reading using weighted relationship. This equation, let us look more closely. In this equation, θ Theta D is a soil measure estimated for D depth of soil based on a couple of top and bottom sensor reading. Theta 1 and theta 2 are ecoflux top and bottom sensor reading respectively. D1 and D2 are soil depth applicable to ecoflux top and bottom sensor reading. And soil moisture was estimated for 500, 600, and 700 millimeter soil column, and ETA was also estimated accordingly. For this, we had used different depth of soil to represent ecoflux top and bottom sensor reading. Our previous study shows that to estimate soil moisture for 500 millimeter soil column, we should use D1 equal 350 and D2 equal 150. That is, ecoflux stem's top sensor should represent 350 millimeter of topsoil, and ecoflux bottom sensor should represent 150 millimeter of bottom soil. Similarly, to estimate soil moisture for 600 millimeter soil column, ecoflux top sensor should represent 350 millimeter soil column, and ecoflux bottom sensor represent 250 millimeter of bottom soil. And to estimate soil moisture for 500 millimeter soil column, ecoflux top sensor and bottom sensor represent 350 millimeter soil column. Reference evapotranspiration was estimated using Krupp-Watt model that uses Penman-Montes methods based on climate data collected from Broadfield weather station. Once reference and actual evapotranspiration was estimated, then Krupp coefficient of Pasteur, which is a ratio of ETA to ETR, was estimated for different growth stages. Pasture height was measured on each 20 lysimeters on daily basis. That helped us to produce a relationship between crop coefficient and pasture height. As we know, individual lysimeter represents very small area, that is only 0.2 meter square surface area. So it might not be justifiable to extrapolate the result from one lysimeter to a large area. Similarly, the results from one group of 10 lysimeter represent only one field characteristics. Therefore, to represent wider field condition, all the data measured from 20 lysimeter were lumped together as one group and result were analyzed. To identify the relationship between crop coefficient and pasture height, we tested linear, power, and exponential relationship, where linear relationship was the preferred option. In this picture, the first figure shows a relationship between crop coefficient and pasture height with regression coefficient 0.43. The second picture shows a relationship between crop coefficient and pasture height with regression coefficient 0.35. And the last figure shows a relationship between crop coefficient and pasture height with regression coefficient 0.24. As we can see, every time coefficient of regression is low. And this low R square was attributed to the way how soil moisture was estimated. For all 20 lysimeters, same ecoflux soil moisture information was applied because it was the only available information in the field. In fact, such constraints are obvious upon many irrigation farms. However, though R square was not very strong, when 500 millimeter soil depth was considered in water budget equation, that improved R square for plant height and crop coefficient relationship. This indicates that in this farm, pasture root depth that plays major role in water budget occurs predominantly in top 500 millimeter soil depth. Thus, irrigation need for this farm should be calculated based on 500 millimeter depth. In other words, to estimate irrigation requirement, we should use effective root depth of 500 millimeter, which has a potential to reduce applied irrigation, improve irrigation efficiency, and thus reduce leaching of nutrient to our water bodies. Thank you for your time.